thank you. This is my first time in this city, and I have been to Poland many times, and I'm very excited by the scientific establishment here. And in fact, today, I realized that this is a celebration of Smoluchowski, and I changed the title of my talk. So I'm going to talk about something related to Smoluchowski and his role in the development of the physics of information processing, especially the Maxwell-Demon problem, which he pretty much solved in 1917, and then the solution got forgotten, or partly forgotten, and it was an instructive example of how progress in one field of science can slow down the progress in another field of science. And all those fields are part of what we now call the physics of information. So I'm going to talk about how, let's see, this is going just perfectly. I'm going to talk about, yes, yes, that's the, yes, I've got, yes. I'm going to do this thing here, too. I'm going to give myself a laser pointer. Okay, good. I can point with the, see this? I can make it move up there without even, yes, that's really amazing. Okay, so, physicists and mathematicians and engineers, as we could tell from our previous talk, they developed their own ideas of what is a sound idea, or a fruitful idea, of an adequate solution to a problem. And this works well in their own field, but in the really now I would say a little over century or 1.5 century long field of integrating the physics with information processing, it took a while to work out the right way to do it. And this is most strongly illustrated by the founders of the science of communication and computation, people like Turing and Shannon, who used classical physics when quantum physics was already well understood. They thought the quantum physics part was just an unnecessary complication. They also ignored thermodynamics, and I'm going to talk about both of those things, how ideas from thermodynamics and quantum physics were brought in to enrich the science of information processing. Now, I'm a physicist, but the theoretical computers, as you know, theoretical computer scientists think they're superior to, theoretical physicists think they're superior to experimental physicists. This is also true in all sorts of other areas. The theory people think they're more important. And some of the most arrogant people of all are the theoretical computer scientists who think they could pretty much solve any other problem if somebody could only manage to state it exactly in terms that they understand. Beginning around the 1960s, a few physicists tried to say that there were some things about information processing that were not adequately captured by the formalism of Turing and von Neumann. Von Neumann should have known better because he busied himself with a lot of physics, but by the time he started working on computers, he forgot about that. Anyway, my colleague Gilles Brassard was one of the first people who was educated as a computer scientist who began to take these ideas, the physics ideas, seriously. Well, anyway, like other parts of mathematics, information science originated as an abstraction from experience. And this abstraction was the fruitful abstraction that Turing and Shannon made was not only Turing, but the people, Turing and Post and Church and so on, was the idea of a universal hardware-independent notion of computation. And Shannon made an even more draconian simplification. He wanted to develop, it did develop a theory of communication by separating the idea of a meaning, of message, from the idea of meaning, which to this day some people think is a big mistake. But it was a very productive, I don't think it was a mistake. But now we know that, as I say, these notions are known to be too narrow, and there are some ideas which people had thought of as physical ideas, but they really belong in the mathematics of information science. And the two, we can see these ideas here in this slide, which is it's based on a slide my mentor at IBM, the late Rolf Landauer, drew about the relation between the physical world and mathematics. Now, Landauer was a big believer in the physical world being really primary. He says information is physical, and he took that to mean that any kind of idea having to do with information that you couldn't think of a physical embodiment of, such as the 2 to the trillionth digit of pi, was really hardly worth thinking about and needn't have any mathematical regularity to it. On the other side, we have Wheeler's it from bit, the kind of mystical idea that information is the foundation of physical reality. So I'm going to talk about two of these rectifications of the over-abstraction of information science. The first one, I'm going to talk about them in reverse chronological order. The first one is the notion of quantum superposition, bringing that back into information science. And the second one I'll talk about is reversibility, bringing thermodynamics back into computation. Well, now, conventionally, information carriers were thought of as what a physicist would call a classical system. Their states are, in principle, reliably distinguishable, and to specify the state of a compound system consisting of two non-interacting parts, it is necessary and sufficient to describe the state of each part. Now, that's known to be not true of atoms, even back before Turing and Shannon both. It's known that to observe a quantum system's state in general disturbs it, and that two particles who are not interacting can be in an entangled state. But for most of the 20th century, information technologists, even those who were aware of quantum theory, regarded the quantum effects as a nuisance because of the uncertainty principle, which would make tiny particles, like for small transistors and so on, behave less reliably than the classical ideal. But now it's known that these quantum effects have positive consequences, making possible kinds of information processing that cannot be done classically. And these are chiefly due to entanglement. So I'll talk a little bit about these things, which probably many of you understand, but in the language of quantum information theory, which has been developed over the last 30 years, roughly. And maybe if you do understand it, you can use it as some of the metaphors that I've developed for explaining it to non-scientists, people who begin to lose interest if you write even one equation. So how do you explain quantum information? Well, everybody understands ordinary information. We use it all the time. But quantum information is more like the information in a dream. You can, if you try to describe your dream to somebody, you end up changing the dream and remembering only what you said about the dream, not the original dream. And the dreams are very private. You can't prove to somebody else what you dreamed, and you can lie about them without getting caught. But unlike dreams, the quantum information has a well-defined mathematical basis. And so, despite these differences, there are important similarities when you start talking about distinguishability of quantum states in the same way as you would think of abstracting the notion of distinguishability for classical states. And that is that just as all classical information processing is reducible to actions performed on bits 1 and 2 at a time, so all quantum information processing is reducible to actions performed on 1 and 2 qubits at a time. And of course, the fundamental principle of quantum mechanics is the superposition principle, which is that between any two reliably distinguishable states, there's a continuum of other states that are not reliably distinguishable. And the motion of a quantum system is a distinguishability preserving dynamics. This can be illustrated, I usually illustrate this with the behavior of polarized photons. So we can have a stream of horizontally polarized photons coming into a calcite crystal, and they go straight through, and the vertical photons will get deviated. And so you can use each photon to carry a bit. But if you give it a supply of identically prepared diagonally polarized photons, they'll behave unpredictably, and some of them will become horizontal and some of them will become vertical. So this was one of the big mysteries about quantum mechanics that Einstein didn't like, that identically prepared systems would behave differently. So this also gives rise to another feature, which is that simply by rotating this apparatus, you can use a rectilinear or vertically oriented crystal to perfectly distinguish vertical and horizontal photons, and just rotate the crystal by 45 degrees, and you can distinguish the two 45 and 135 degree polarized photons perfectly, but there's no way of distinguishing all 4 kinds. This is not the way classical systems behave when you measure them. In fact, my frequent collaborator, Bill Wooters, who teaches at an undergraduate institution, has taught young people for many years. He has a good analogy for how quantum systems behave when you measure them. He says they're like the system is like a student, and the measuring apparatus is like a teacher in one of those old-fashioned schools where the students weren't supposed to say anything except answering the teacher's question. They were not supposed to speak up. So the teacher says to the student, are you vertical or horizontally polarized? And the student says, I'm polarized at about a 55 degree angle to the... I believe I asked you a question. Are you vertical or horizontal? Horizontal, sir. Did you ever have any other polarization? No, sir, I was always horizontal. So this peculiar behavior of quantum systems is the thing that probably one of the first people to discover or to appreciate this was Stephen Wiesner, who said, you got to be able to do things with this that you can't do with classical information. And one of the ideas that he came up with was quantum money, which in principle can't be copied. If anybody can read Latin there, the slogan says, "I shall not be duplicated." So it has 20 photons in perfectly reflective boxes, which of course is impractical. In fact, if you tried to make a piece of quantum money, it would be about the size of an automobile and much more expensive, and it would decay within a few minutes, and so it would only be good in a country with rapid inflation, because you'd have to spend it before. Well, anyway, this same idea was used by Gilles Brassard and me and other people also to develop quantum cryptography, which is a somewhat more practical idea, although our first implementation of it was able to send secret information over a distance of about 30 centimeters. Now it's done, I guess they do it in China over 1,000 kilometers. Well, anyway, getting back to the information science, taking away everything extraneous that having to do just with a particular implementation, but not with the information, any quantum data processing can be done by 1 and 2 bit qubit gates, and here's an example of it. Of course, a 1 qubit gate is just a rotation of a polarization if we're considering polarized photons. A 2 qubit gate is a conditional 90 degree rotation. it's the quantum analog of the exclusive OR gate. And because it's quantum, a superposition of inputs, which is the diagonal is equal to a linear combination of horizontal and vertical, gives you a superposition of outputs, which already is an entangled state. And what is this entangled state? How can you describe it? Well, an entangled state between the state that equal superposition of both photons being horizontal and both vertical is not the same as each of the photons being in that superposition. It does happen to be the same as the superposition of both diagonals and the opposite diagonal. So you could say the photons are in a state, a definite state of sameness, even though neither photon has a polarization of its own. So that's the fundamental, simple but hard idea that underlies entanglement and is inseparable from quantum theory. Well, one of the nice properties of entanglement is monogamy, and that is that if two systems are maximally entangled with each other, they can't be entangled with anything else, or they can't even be classically correlated with anything else. And indeed, classical correlation, which our world is full of, I'm trying to give you some correlation of what's in my mind by talking to you. Of course, classical correlation can be broadcast to large audiences. But it comes from, you might say that it always comes from a failed attempt to clone entanglement. Quantum information can't be cloned, but if you try to do it, this is what happens instead. So let's view it in terms of this sort of social analogy. Alice and Bob become entangled because Alice is in the superposition of vertical and horizontal, and Bob starts out horizontal, and then he becomes perfectly entangled with Alice, so he's aligned with whatever direction she is, even though neither of them has a direction. But Bob, being a kind of a gregarious kind of guy, he goes and decides to also get entangled with somebody else. I guess I'll call her Judy here. So he does the same thing down here, and then pretty soon he finds that his entanglement with Alice has been spoiled, and also he doesn't get any good entanglement with Judy. He's just classically correlated with each of these other characters. And in fact, what he does, he ends up being perfectly entangled with the now non-trivial relationship between his two girlfriends, which I would say is an appropriate punishment. Anyway, that's the way entanglement behaves. And we can think of that as understanding the origin of quantum randomness. Let's look at this experiment up here. And let's take away the measurement at this end. Let's say we don't measure the photons, and we instead, if you don't measure them, and this is pretty orthodox quantum mechanics, their random behavior can be undone. It's not even really behavior. We put in a half-wave plate here, which converts the horizontal photons to vertical and the vertical to horizontal, another crystal of equal thicknesses, and the two beams recombine and recover the original polarization. So when the student said, I was always horizontal, something happened to him which you can describe in terms of entanglement. And this, it would be more or less saying that because he had to disclose his polarization to a large audience, the public embarrassment of having to say his polarization in front of the whole class made him forget his original polarization. So we can express classical data processing in quantum terms by just saying a classical bit is a quantum bit with one of two standard distinguishable values, and a classical wire is any channel that carries those faithfully, but spoils their superpositions. And the reason that happened is the typical classical wire, it's hard to keep it away from other systems that eavesdrop on it. So a classical wire is a quantum channel with an eavesdropper. And if you lose track of the eavesdropper, here, let's say the signal interacts with an eavesdropper who tries to copy it, generates an entangled state, and the entangled state gets lost in the environment where you can't recover it. A classical channel is a quantum channel with an eavesdropper, and a classical computer is a quantum computer with eavesdroppers on all its wires. So people are always asking me, at IBM especially, how is it that quantum computers have this exponential speed up for some problems. And if you can find an exponential speed up for some problems, why can't you give me an exponential speed up for all problems? What's the matter with you? Can't you discover any more quantum speedups besides the 2 or 3 or so that we know already? And my answer to them is there are no quantum speedups, there are only classical slowdowns. And most computations are not harmed by eavesdropping, but some are, just a few. So maybe there are no other quantum speedups. But it's such a different a way of looking at information, and this new way of thinking of it has led to a whole classification of quantum versus classical computational complexity classes, which is really quite now mature and fruitful. So if entanglement is ubiquitous, how come it wasn't discovered until the 20th century? And not really appreciated until the last half of the 20th century, except by Schrödinger, who was really impressed by it about 1935, but nobody much listened to him. And the answer is because of the monogamy. Most systems in nature, other than tiny ones, interact so strongly with their environment they become immediately entangled with it, which destroys, it makes the entanglement hard to see. Now we'll go on to the other problem, the reversibility, and this is the thing that has to do with Smoluchowski. Now the analogy between computation and physical dynamics, physical motion, under laws of motion, is really a very old idea. For example, Galileo's The Book of Nature is written in the language of mathematics. And especially Laplace's famous description of the universe as a kind of a entirely predictable clockwork, which I can't put it better than, of course, it's probably even better in French. But anyway, this expression has been well translated into all languages. It's interesting now that the kind of computation he's talking about is a reversible computation, which is not too different from a physical dynamics. It was a very similar then. So the thermodynamics I'm going to talk about, one of the most exciting things about the second law of thermodynamics is how many seemingly different manifestations it has. And these are just a few. The two famous ones are the Kelvin and the Clausius statements of the second law. And the Kelvin statement has been rendered into a nice song by the British comic duo Flanders and Swan. Have you ever heard, who here has heard that? Heat cannot of itself pass from one body to a hotter body. It goes on. Heat is work and work's a curse, and all the heat in the universe is going to cool down because it can't increase. Then there'll be no more work and perfect peace. Anyway, it goes on like that. Then this is another one that many of you probably are familiar with, the fact that you can't see anything inside a uniformly hot furnace by the light of its own glow. Another one I thought of is ice skating, which is possible because ice floats and it melts under pressure. And then the one that has to do with information processing is Landauer's principle, which was the best expression of it was not due to Landauer but to Benjamin Schumacher, and that is and it's by analogy to the Clausius statement. No physical process has as its sole result the erasure of information, and this is, I would say, this was an idea that was well understood by. Pretty well understood by Smoluchowski. It was not clear how well Maxwell understood it. I think if you read over his description of his demon paradox, you wonder why it didn't bother him more. I don't know if I have it here. Yes, here's the Maxwell demon in his own words from 1867. You've probably all heard of this idea. If a small being was able to open and close the door between two halves of a room and allow only the fast molecules to go in one direction and only the slow in the other, he would produce a violation of the second law. And how is this contradiction avoided? Well, Smoluchowski wrote about it in 1912 and pretty much answered the question. He said, well, let's take away the demon as an intelligent being and just sort of think of a simple kind of mechanical apparatus that would do that job. And let's not talk about selecting the molecules according to the temperature or the speed of motion. Let's just select them by a one-way valve, like the kind we use in machines of all sorts. So we have, imagine a box with a partition down the middle, and in the middle there's a trap door that can only open to the right, and it's held in place by a weak spring. So when a molecule strikes it from the left, it opens the door and comes into the right. And eventually, most of the molecules will come over here, and we'll get high pressure gas on this side and low pressure gas on that side without doing any work. Well, Smoluchowski presented this model and then solved it and showed why it wouldn't work. The reason it wouldn't work is that for this door to be light enough and weakly sprung enough that a single molecule can push through it, the door itself will undergo thermal motion. It'll undergo Brownian motion. It'll be swinging randomly open and closed all the time. And some of the time, if a molecule wanders in front of the door will swat it through like a baseball bat in the opposite direction. And he calculated that those two processes would happen at exactly equal rates, and so it would be completely ineffective in sorting the molecules. And so that was, I would say that pretty much solved the Maxwell-Demon problem. But, and this is where I get into the kind of the you might say the herd instincts of scientists. They like ideas that are successful, and they lose sight of ideas that somehow don't seem to fit. And they all think the same way. So despite, and they forget the thoughts of scientists even 50 years earlier. So despite Laplace's deterministic universe, and I guess you can't blame Smoluchowski for, well, not Smol, I'm going to blame other people. I'm going to blame Dillard. And despite what Turing and Gödel were about to find out about computation, the early 20th century physicists were reluctant to think of thinking as a mechanical process. And so the great paper, and rather maybe even more famous than Smoluchowski's paper, is Leo Szilard's 1929 paper, which had this kind of a confusing title, or it's a title that sowed confusion for several decades afterwards. It was called On the Decrease of Entropy by the Intervention of Intelligent Beings. So that sent people down the wrong track for a while. And this was further muddied by the discovery of quantum mechanics, which showed everybody that measurement was not a simple process that they'd thought before. It was some kind of measurements were incompatible with other kinds of measurements, and people jumped to several physicists, good physicists, jumped to the incorrect conclusion that therefore some measurements were possible but had an irreducible thermodynamic cost, which is what prevented the demon from working. Now, Szilard was not one of these. In this paper in which he introduced his ingenious Dillard Engine, he did the mathematics correctly, but the words he used about it led other people astray because they didn't bother to follow his mathematics clearly. And I would say the person who brought some order to that was Rolf Landauer, who in 1961 correctly identified the information destruction rather than the acquisition as the fundamentally costly act. And to show you how this works, I'll show you the Dillard engine and why it doesn't work. The Dillard engine was an engine that had a gas that consisted of one molecule, and the idea was the gas was allowed to roam freely in the cylinder. The cylinder has a piston at each end, and a measurement, first of all, a partition is inserted and it traps the molecule on one side or the other. That doesn't take any work. Then the demon or the mechanism operating the engine, ascertains which side the molecule is on, makes a measurement. So it starts off in a standard state and it ends up in a state R, meaning the molecule's on the right, or in this case, an L state. So the R state and the L state are two distinguishable states of the measuring apparatus. And then based on those two different states, a piston is inserted on the empty side, the middle partition is removed, and the molecule is allowed to do work against the piston, expanding it back to the full size. And this produces kT log 2 of isothermal work, and then you just do the thing over again, and you get unlimited amount of work from heat, violating the Clausius principle. Well, the reason it doesn't work is if you explore the joint configuration space of the atom along the horizontal coordinate, and the states of the memory, where the memory has three states, the left state, the standard state, and the right state along the vertical coordinate, all you're doing is moving this volume around in phase space until you get to this part where you're allowing it to expand, and then you have to take these two equal volumes and compress them down to half size, which is costing as much work as you got out. So that's why it doesn't work. So the kind of sloppy thinking that occurred following quantum mechanics was Leo Brillouin's 1956 argument that to even see the molecule, the demon would need to illuminate it with at least one photon of light of more than thermal black body radiation, which of course is quantized. And then the most elaborate mistake or unnecessary refutation was the high compression engine designed by Denis Gabor. And here it is. It's a beautiful engine. The way it works, it's a very, very long cylinder, and the bottom of it is transparent, and there's a light beam, which the idea was he didn't have lasers then, and so you imagine you set up a light beam by some process that just circulates here losslessly between perfectly reflective mirrors and perfectly transparent lenses until the molecule wanders into it. And when the molecule wanders into it, a mechanism is activated which pushes this piston in here, and of course the light beam has been extinguished. And so then you let the molecule do work against the piston, and you get an unlimited amount of work, or an arbitrarily large amount of work, just by making the cylinder very long. So however much work it takes to reset this trap to catch the molecule, the demon just gets more work out by making the cylinder longer. And so the question is, what keeps it from breaking the second law? And I can ask you two answers. Can you guess Gabor's answer, which is hard, or can you guess the correct answer, which is easy? Who wants to try? Well, I'll tell you the answer. I'll tell you the easy answer. The easy answer is, as you all know, there is nothing entirely irreversible in nature. Think of a mouse trap. This is a trap, it's an optical trap, but it's a trap designed to catch a molecule at one part of a large volume. Now, a mouse trap pretty much does the same thing. You put a mouse trap and it catches a mouse, you think, irreversibly, and it doesn't matter how big your house is. The larger the house, the longer it takes the mouse to wander into the trap. But as soon as it hits the trap, well, that's the end of the mouse. This is not true. As you all know as physicists, if the house was really very large, the reverse process of the mouse, the dead mouse, fluctuating into a live state with its bones not broken anymore, and the thing that just killed it in the trap lifting up and letting it walk away from the trap, has a very slow rate of happening, And if you make the house exponentially large compared to that energy, the trap will function in reverse, just like Smoluchowski's trapdoor. So that's the reason this doesn't work. But that's not what Gabor said. He said it has to do with the quantum nature of light. And in order to create this light beam in a very large cylinder, such that the light is concentrated at one end of it, you need to use at least one photon from each of the optical modes in the cylinder, which get more and more modes than when the cylinder gets longer. That's all true, but it is unnecessary and insufficient to explain why this thing doesn't work. So that's an example of how a successful idea in one part of science can lead to slower progress in other parts of science. So another thing that probably, let me ask all of you, I'm going to try to get a yes or no answer from everybody here. So those of you who don't raise your hand when I ask you for yes, I'd like to hear you see your hand on the other one, on the no. So how many of you think information is valuable? Is a good thing? All right, well, most people seem to think that. I won't ask the other ones. Landauer's principle is a little hard to describe. That is, that information is costly to dispose of, because most people think information is a good thing. But actually, it's a little bit more like glass and plastic. It's useful, but then there's a problem of disposing of it when you don't want it. And Landauer showed various reversible ways of processing information, and some irreversible ones that you have to use if you. He was talking about handling information by modulating a bistable potential well. A little gray dot in here is supposed to represent this. This is a 0, this is a 1. If you want to change a 0 to a 1, the usual way, say in a magnetic memory, is to apply such a strong field that the 0 state becomes unstable and it falls into the 1 state, then you reestablish the bistability. But there's a more gentle way of doing it, a reversible way of doing it. But if you have to restore both a 0 or a 1 and you don't know which it is to the 1 state, it costs kT log 2 because you have essentially allowed this molecule to escape into the big cylinder without getting any work out of it, and then you're squeezing it back to the lesser volume. So, as you know, computation is in principle reversible. And why is there therefore the need or the desire to erase these garbage bits? And the answer is that, and this is true also of quantum computation, is that it's just sometimes a convenience. So here is something that you know that you can embed any quantum computation in a reversible one, where you do it as a unitary operation, you look at the answer, and then you undo this operation, and you can get out this value. So you haven't changed anything, and it hasn't cost you anything thermodynamically. Well, now, the reason you do this is that if you want a quick and dirty way of getting rid of the unwanted data, even if it costs you. And it's very much analogous to throwing away. Here, what happens if I put the green spot right on top of the red spot? Okay, well, anyway. It's like throwing away stuff that you could have, say, recycled if you had had more patience or time. Okay, so where did I go here? Yes, I would say the integration of physical, especially quantum ideas and methods, has been fairly successful in the theory of information and communication. But in the 21st century, cosmology is offering some new challenges and opportunities for this intercultural synthesis and friction. Observational astronomy strongly supports what's called a standard model, which includes the apparent fact that our universe is expanding at an accelerating rate. That is, that empty space has a property called dark energy, an inherently self-repulsive sort that gravity opposes but doesn't overcome. And so this leads to the ultimate state of our universe in the far future is very empty and expanding at such a rate that from any point in this space, there is a horizon at a constant distance, a constant large distance, beyond which anything further out than that is departing from us at greater than the speed of light. Now, this leads to a problem of whether we should believe any of science's predictions, which is called the Boltzmann brain problem, and I'll talk about that. And then at the very end, I'll talk a little bit about the Wigner's friend problem, which is related to it. So I'm just going to say, well, our world is pretty complicated, but it kind of helps to say what we mean by this kind of complexity. So I'm going to look at a really simple, classical, discrete model of physical dynamics. This happens to have a conserved energy function. It's a one-dimensional cellular automaton. So time is going from left to right or from right to left. It's the same rule. And the space is this one-dimensional array. And I've started in a periodically repeating condition but with a little defect here. And you see it produces this deterministic but complicated, increasingly complicated wake, like the wake behind a boat, as time goes on. And the rule is just a deterministic Ising model in one dimension with an interaction with the first and second neighbors, reversible interaction. So what do we mean when we say the situation gets more complicated? The state gets more complicated. And I tried to formalize this with a notion that I call logical depth. And it begins with the idea of Occam's razor, which actually was much better stated by Aristotle than by Occam. And that is that if you have alternative hypotheses to explain a phenomenon, you should choose the most economical hypothesis, regardless of the amount of computation and deduction that has to go between the hypothesis and the thing it explains. So that says that in this case, we have these several hypotheses, and we should choose this most economical one. But of course, this is a principle that scientists most often use to argue that their theory is simpler than this newfangled theory that somebody is presenting that they probably don't even understand. Well, that just shows how complicated it is, so forget about it. So it's often used to impede science. So what you need is a way to compare the economy of hypotheses in a disinterested way. And that is provided, as so many other things in our world, by digital computation. So we digitize the phenomenon, we digitize the hypothesis, and we digitize the process of deducing the phenomenon from the hypotheses. The phenomenon becomes a bit string. The hypotheses become inputs to a standard universal computer, and we say, well, the most plausible explanation is the smallest input that causes this computer to exactly generate this as an output and then halt. Well, so one of the outputs that do that would just feed the thing itself as input and say, do this, print this, and stop. So that's a kind of a non-economical description, and here's a more economical description. So what that says is that the shortest program in number of bits is the most plausible, and you might say that the size of that program is the information content. This is well known as Kolmogorov information, or algorithmic information, the information content of the object that it explains. But I'm focusing not on the smallest one. I'm saying, well, let's not think about the size of the smallest one. Let's think about how many computational steps it takes to go from here to here. That's the plausible amount of number crunching that went into the generation of this object, and I call that the logical depth. So a trivially orderly sequence, like a lot of ones, is shallow because you can make it fast from a small program. A random sequence is shallow because it's its own shortest description, and so on. So it has the right properties. And in this case of a physical dynamics, gradually getting more and more complicated, you would say the logical depth of this increases because this thing, or even a good-sized piece of it, contains enough evidence to infer this as a plausible causal history of it. But if you let this dynamics run a very long time, of order of the Poincare recurrence time, the configuration becomes very random looking, subjectively, and very shallow. Or put another way, the simple example of an explosion in a room. If I confine all the air into a little space here, and thinking in terms of classical, perfectly reversible classical dynamics of Laplace, an hour later, the sound of this explosion will have died out. The gas will fill the room pretty uniformly, but those molecules are still in a very special state that contains evidence of having had an explosion an hour ago. But if you wait for 2 to the Avogadro number of seconds after the initial condition, it will be a typical configuration that will not have particular evidence of that history. And it won't have the evidence for this long reason, for this sort of mathematical or computer science region. And that is that the shortest description doesn't involve saying how long you have to run the dynamics, because that number itself takes around Avogadro's number of bits to say. And therefore, the true history has lost its persuasive evidence that that's what happened. Now, conversely, I'm going to skip ahead a little this. Conversely, and this is sort of true of the world in general, if you let a system run for a long time, the true history cannot be reliably inferred from the present state. Conversely, a structure that seems to be complex and deep might have just been produced by an unlikely thermal fluctuation. And this is the Boltzmann brane problem. A friend of Boltzmann said, well, maybe the universe is low in entropy, or at least the part that we live in is low in entropy, because the actual universe is very large and at equilibrium, and we happen to live in a part that has fluctuated out of equilibrium, which is easy to explain because if it were still at equilibrium, we wouldn't be here to complain about it. And so this nicely explains the out of equilibrium situation we observe and the arrow of time, but it over-explains it because the most likely fluctuation is one that just produces something the size of one person's brain. And the rest of the universe is in a chaotic state. And so this brain would, for a short time, have think that it was surrounded by an auditorium of other people and think that there was a lot of scientific evidence for the universe being 14 billion years old, but those things would all be illusions. This was, and serious cosmologists worry about this because, as I mentioned, the standard model of cosmology says that our world is going to go to an infinite future at positive temperature, which means that all these fluctuations have an infinite amount of time to happen. And the idea that we're in the youth of a real universe rather than a fluctuation in an old dead universe has lost its persuasiveness mathematically. And this was nicely explained by Sean Carroll, one of the authors of that paper. He says, imagine that the universe is at equilibrium here, and it has these little fluctuations, very large. This is Boltzmann's picture. He didn't even know about the expanding universe. He was just thinking of a classical universe at thermal equilibrium. And it gets little fluctuations, and a little fluctuation this sort is big enough to make a brain in it. And of course, we think that we're on the downside of a relaxing large fluctuation of 14 billion years ago, and we're down here, and there's still a lot for it to go before it gets to be maximally random again. The problem with that is that conditioned on everything we observe now, the most likely explanation for our past history is not the fluctuation that would give us this 14 billion year history, but the minimal size fluctuation that would give us what we have today, or which would give even my head what I have today, with the rest of you just being illusions. So that's the Boltzmann brain problem, and it's a problem that afflicts cosmologies that predict that the universe will have an infinite future at positive temperature. Or even finite cosmologies, such as any system described by a Hamiltonian, classical or quantum, in a finite-sized box, because it will equilibrate eventually, and on that you would say classically, the equilibrium orbit in phase space, false recurrences, in which the recurrence of the size of a person's head occur, but not the whole world they think they see, will vastly outnumber true recurrences. So that's a problem. What Sean Carroll calls it a cognitive instability. If you believe the theory, then one of the predictions of the theory is that you shouldn't believe it. This was actually the idea of a mechanical system coming to equilibrium occurred in the 19th century, and people worried about it. They called it the heat death of the universe, but they thought it was a problem for the distant future. But actually, it's a problem for any system that equilibrates to positive temperature, which is a great many of the models considered in physics. If you think you live in a world like that, you have to find some additional reason to explain why your perceptions are real. And cosmologists worry about that. Now, the Wigner's friend problem is a simpler and gentler version of Schrödinger's cat. Wigner's friend is someone that Wigner postulated. He says, well, I suppose I have a friend who performs a quantum experiment with two outcomes, but doesn't tell me until later. So what is the state of the friend after the experiment is performed, but before he tells me? And the answer is, well, he's in the superposition of two states, just like Schrödinger's cat, except that he doesn't realize it. And then when you look at him, then he becomes one or the other. So this sounds like, well, maybe it's not even a problem. It's just like a problem, a puzzle for philosophers to worry about, any more than that, like which interpretation of quantum mechanics do you want to believe? But cosmologists have started worrying about it, because in the sequel to this 2013 paper that I mentioned, the same authors, joined by a third one, argue that it is not necessary. Oh, they argued, by the way, in order to get rid of, in that 2013 paper, this is a typical scientist's reaction to things, to get away from the Boltzmann brain problem, they supposed that if the Higgs boson had a certain mass, that the universe would self-destruct by way of a vacuum fluctuation before there got to be any Boltzmann brains. So this was solving the problem of the Boltzmann brain by getting rid of the universe. But they decided that was not a good explanation after all. And they argued instead that the thermal state of the universe at the end doesn't have any Boltzmann brains in it, because there's nobody there there's no measuring apparatus there to record it. And so that the idea that the experience of someone within a universe doesn't become real until an irreversible act of measurement has occurred. Now that's quite controversial, and in fact it splits the culture of general relativists and cosmologists from the culture of quantum information theorists. The quantum information theorists say, well, of course, a mixed quantum state is compatible with any collection of pure states that have it as a density matrix. And the cosmologists say, well, the thermal density matrix is stationary, therefore nothing can be happening in it. How's my time, by the way? Oh, it's over. Well, I'm over too. That's an example of an unsolved paradox where we're trying to understand physics, and something about how you think about it and which culture you apply is still to be worked out. Thank you, and I'm sorry if I've gone on too long.
Yeah. Thank you, Professor Bennett, for very, very nice talk.